unit photochemistry, and the fourth part of that is kinetics of collisional quenching, that is Stern-Volmer equation. Basically, we have seen the collisions in solution, and based on that collision solution, the next part is Stern-Volmer equation. So firstly, what is quenching? Quenching is nothing but the decrease in the fluorescence intensity. As we know, when the fluorescent molecule or the excited molecule which is in the first singular state, it is coming to ground state. At that time, the light which is it is emitting, or the radiation which is it is emitting, that are the fluorescent radiations, and decrease in those fluorescent radiation are called the quenching process. Is being called as the quenching process. It means a molecule which is being in the excited state, it is having its spontaneous emission, and when it is coming to the ground in the presence of some quencher, there will occur some decrease in that fluorescent intensity. So a quenching process is defined as one which competes with the spontaneous emission process and thereby shortens the lifetime of the emitting molecule because of the presence of quencher there. So we have seen there are mainly four types of quenching, and out of those two are static quenching as well as the dynamic quenching. In static quenching, it is a strong coupling exists between the fluorocer and the quencher, where the fluorocer and quencher may combine and form the complex in the ground state, while that of in dynamic quenching, the fluorocer, which is the excited molecule, we will call it as fluorocer. So the fluorocer molecule will give its excess energy to the quencher, as a result of which the quencher will get excited. So let's see next. So the decrease in the fluorescent intensity is quenching process, and these quenching reactions, they may be energy transfer reaction, as we have seen in dynamic quenching, it is transferring the energy, or there may be the, when it is forming the complex in ground state, it may be the electron transfer processes. In some cases, the complex, as we can see here, in case of static quenching, the complex is being formed in the ground state. There may be the possibility that the complex may be formed in the excited state also, and that excited state complex are called as exciplexes, and those complexes may be or may not be emit radiations. Means they will have the possibility to emit the radiation as well as not to emit the radiations. It is based on the conditions. So in solution, as we have seen the collision in solution, what happens there? Basically, the Na plus and Cl minus, which are the two solid particles, they get surrounded by the solvent cage. And if let's take the fluorescent molecule is inside the inside solvent cage, as well as the quencher is outside the solvent cage. So what will happen? The quencher will come inside the solvent cage, and after coming this inside the solvent cage, what will happen? There will occur the formation of ground state complex. So the fluorocer, which is given here as R, and the quencher, that is Q, they will combine together and form a RQ complex. So the fluorocer, this is same, the quencher will come inside the solvent cage, combine with the fluorocer, and will form the ground state complex. And this is the example for electronic energy transfer, as well as it is called as the static quenching. And since there is no emission competition between the emission process, because it is being coming, the quencher is coming inside the solvent cage, so there is no competition between the fluorescent molecule as well as the complex formed. So here in case of static quenching, remember this sentence or this statement, that here in this case of static quenching, it is the lifetime is not affected. What is lifetime? When the molecule is coming from higher excited state, that is, it may be coming from S2, S3 state, from S2 it is coming to S3, from S2 it is coming to S1. So these are the internal conversions, or as well as it may come from S1 to triplet state, and this will be called as the intersystem crossing. And from then it will come to the ground state. So there will be the two steps, that is internal conversion as well as intersystem crossing, and when it will come from that S1 state to S0 state, then it will be the fluorescence. So in that case, the lifetime of the fluorocer is not affected in case of static quenching. As well as we can see here that in case of static quenching, there is no role of diffusion coefficient here also, which is being played in case of dynamic quenching. So here we can find that the ground state complex form reduces the fluorescence intensity by competing with the uncomplex molecule for the absorption of incident radiation, and this is similar with that of those where we add some substances in order to decrease the fluorescent intensity, and this is called as the inner Zilter effect, because the quencher is coming inside the solvent gauge and it is forming the complex with the fluorocer and decreasing the fluorescent intensity. So as it is coming within the solvent gauge, so it is also called as the inner Zilter effect. Now if the molecule is being steadily if the molecule is being under steady illumination, then in that case the rate of formation of the excited molecule will become equal to the rate of its deactivation. So as the rate of activation is equal to the rate of deactivation, so the overall concentration of A will remain the constant. Here A naught A star naught is the concentration of the fluorocer in the absence of quencher, and we have seen the rate equations in same one, how to write the rate equation. So from that we can calculate the concentration of the substance. So similarly we will take here and it will come out to be Ia divided by Kf, Kic and Ksc, where Kf is the rate constant for the fluorescence state and Kic as well as Ksc KISC, these are the rate constants for internal conversion as well as intersystem crossing steps, and the summation of KIC and KISC, it will be the summation KT, and these are the unimolecular deactivating steps. Now if the quencher molecule is being present, in that case what will happen, the excess energy of the fluorescent will be given to the quencher, and in that case the rate constant can be given as, the rate equation can be written as Kq times concentration of the products. So concentration of reactants. So here rate is equal to Kq times A naught star into concentration of Q. So here concentration of fluorocer in the presence of quencher can also be written as now Ia divided by Kf plus summation Kt, and there will be the addition of factor, that is Kq times concentration of Q. Now here the respective quantum units can be given as, what is quantum unit? Quantum unit is basically the number of photons emitted to that of number of photons absorbed. It means if the molecule is in, if fluorocer is in the absence of quencher, it will emit some more amount of photons, and if the quencher is present, there will be the decrease in the fluorescent intensity. It means there will be some reduction in the number of photons in the presence of quencher. So the respective can be given by QF naught, that is in the absence of quencher, and QF in the presence of quencher. So what is quantum yield? Number of photons emitted to that of number of photons absorbed. So absorbed radiations, for that they have written Ia, and number of photons emitted, for that it may be the number of molecules destroyed. So it is Kf in bracket of concentration of H star naught. So here placing the value of H star naught, which is equals to Ia Kf plus summation Kt. So you can find that Ia will get cancelled out with the Ia, and the remaining quantity will be Ia. This Ia will cancel out with this Ia, and the term remain will be Kf divided by Kf plus summation Kt. And likewise for the quantum weight in the presence of quencher can be given by Kf A star divided by Ia, and placing the value for A star here also, which is IA Kf summation Kt plus Kq times Q. So what will happen here? IA again will get cancelled out with the IA, and the equation will be remain as Kf divided by Kf summation Kt plus Kq times Q, as you can read that. Now if we go on taking the ratio of these two quantum units, that is the quantum unit in the absence of quencher as well as quantum unit in the presence of quencher. So dividing the two equations, that is 6.89 with that of the 6.8, you will get this expression where Kf terms, this Kf will get cancelled out with this Kf, and the remaining quantity will be Kf plus summation Kt, and the term will go up and it will be Kf plus summation Kt plus Kq times concentration of Q. Now if we take, as you can see, this is summation Kt, these two terms summation Kf summation Kt, and these are two summation Kf plus summation Kt. So they have just simplified the equation as 1 plus Kq times concentration of Q divided by Kf plus summation Kt. If you go on solving this again, you will get the same expression. So this, it is the simplification of the equation. Now let's take that 1 divided by, let's take here it is 1 divided by Kf plus summation Kt. This is nothing but the lifetime of the fluorescent molecule. It means the while crossing through the internal conversion, intersystem crossing, and fluorescent molecule is coming to the ground state. It means that is 1 divided by Kf plus summation Kt is nothing but the lifetime of the fluorescent molecule, and which is denoted by the symbol tau, as you can read here. So you can watch there. So our expression will again get simplified, that the ratio of the quantum units, that is Qf naught divided by Qf, it will be equals to 1 plus Kq times tau and concentration of Q. Again now this 2, that is Kq plus tau, it is equals to 1 plus Ksv times Q, where Kq tau is nothing but a constant which is called as the Stern-Volmer constant. It is just like to that of the equilibrium constant, and this equation is called as the Stern-Volmer equation. What is the equation? Qf naught divided by Qf, it will be equals to 1 plus Ksv times Q. So if you go on plotting this equation in a graph, as I have seen here, I have shown here, here there will be the quantum units Qf naught by Qf, and there will be the x-axis. It is plotted on the x-axis and this is plotted on the y-axis. So 1 will be your intercept, that is C value, and Ksv. So it will be your M value. So this is your value for Ksv. So this is about the Stern-Volmer constant. Now Stern-Volmer constant is basically a ratio of bimolecular quenching constant. As we have seen the equation, that is A star, it is combining with Q and forming A plus Q. That is the bimolecular quenching state, that is K times Q, Kq. So it is, and there is a reaction where A star is getting excited, and then that is the fluorescent molecule which is coming to the ground state and emitting some fluorescent radiation, which is the unimolecular decay constant. So as we have seen in the earlier slide, what is unimolecular decay constant? When the molecule is coming from higher singlet state to the lower singlet state, then it is coming through internal conversion as well as intersystem crossing. So those steps are the unimolecular decay constant steps. So Ksv is basically the ratio of bimolecular quenching constant to that of unimolecular decay constant, and it has the dimensions of liter per mole. Here it implies a competition between two decay pathways, as when the molecule is being undergoing decay, so there will be the two pathways. It means there may be the presence of static quenching or there may be the presence of dynamic quenching, and in case of static quenching it will be the time independent process, while in case of dynamic quenching it is the time dependent process. And also they are, in case of static quenching, the decrease in the fluorescent intensity is dependent on the diffusion coefficient, while in case of dynamic quenching it will be the opposite. It will not dependent on the diffusion coefficient. So we will study that in the next slides. So before that, the Stern-Volmer equation, as I have shown you in graph, it is a linear plot where we will get a straight line, and with the slope of Stern-Volmer constant as slope, intercept as one value, and the mechanism of quenching is operative. Now let's watch a video, and after that there will be the two cases. As we have written here, there is a competition between two decay pathways. It means the mechanism, what will be the mechanism if static quenching is present, and what will be the mechanism is if dynamic quenching is present. Those are to be seen. So have a look on the video.
Kinetics of quenching, right? And we're going to discuss also something which is shown right here, which is a Stern-Volmer plot, and we can determine what can be found or determined from it. Make sure to like this video and subscribe to the channel for future videos and notifications. All right, so what is a Stern-Volmer plot? And then we'll go into this based on our understanding of it. A Stern-Volmer plot is a ratio of this thing right here, which we'll talk about in 1 minute, as a function of the concentration of the quencher. Now, what is a quencher and what is quenching? So a quencher is something that basically stops a quantum event. Okay, in this case, we're talking about fluorescence. So if something quenches fluorescence, it means it stops something from fluorescing. Okay, it might absorb some energy that's required to cause fluorescence. It does something like that, and it just stops fluorescence. Okay, like when you think of quenching in terms of thirst, it stops your thirst. Okay, your thirst is quenched. It just means in this case it stops the fluorescence. Okay, and we're looking here at the concentration of the quencher. Now, when you plot this whole thing versus the concentration of the quencher, it actually yields a straight line. Okay, and like we said earlier in other videos, Pchem is the pathetic attempt to force everything into a y equals mx plus b, a straight line. So what is this thing on the y-axis? Let's break it down. So this Greek symbol, this is our quantum yield of fluorescence. And what is the zero mean? So this numerator is the fluorescence quantum yield in the absence of a quencher. Okay, that's what the zero means. There's no quencher. And that has the expression, the rate constant of the fluorescence times the radiative lifetime of that particular species. All right, and that will give you the fluorescence quantum yield in the absence of the quencher. All right. Now the bottom here, the denominator, this is the fluorescence quantum yield with the quencher. And its expression over here is a little bit more complicated. It's equal to the rate constant of fluorescence divided by, first of all, this term, 1 over the radiative lifetime of the species, plus the rate constant for the quenching times the concentration of the quencher. And notice there is a difference between the case of F and the case of Q. All right, so what we're going to do is we're just going to take the ratio of without the quencher and with the quencher, the two quantum yields. So we're going to take this whole expression, Kf times this tau naught, and divide by this whole thing. Now you'll notice when you do that, I won't show you the algebraic derivation, but notice that you're going to have a Kf here divided by a Kf. So you'll notice in this following expression down here, there's no Kf term, but the Kq, this term does survive. Okay, and when you do this quotient and you simplify it as much as possible, what you'll find is that the ratio of the fluorescence quantum yield without the quencher to the fluorescence yield with the quencher, this is going to be equal to 1 plus this whole term right here, the rate constant of quenching times the radiative lifetime of the species times the concentration of the quencher. Now, for a given species that fluoresces, the radiative lifetime is a constant. This rate constant is obviously a constant, so we've got this concentration of the quencher, which is a variable here, times two constants. So if we know these values right here, we know this ratio, we have a y equals some number plus a number times the other variable. So this is actually not exactly in the form, but it's basically y equals m x plus b. Now our b, which is our y-intercept, is just 1. So that's the nice thing about a Stern-Volmer plot. It actually intersects the y-axis at y equals 1 right here. And then it turns out that if you then plot this y, which is this ratio, versus, assuming x is your concentration of the quencher, the slope of this line, which some sources will denote capital K, that's actually equal to these two numbers that are multiplied in front of the Q, which are the rate constant of the quenching times the radiated lifetime of the species. And so typically you would get a graph like this, and they might say determine the Stern-Volmer constant. Now the Stern-Volmer constant is actually just the slope of the line, which is simply the K. But if you know what the radiative lifetime is of the species is, which you can look up, you can actually then determine the rate constant for the quenching. Okay? And that's the main thing that you can actually determine from a Stern-Volmer plot. Okay? We may actually do a practice problem of this in the next video. So hopefully this actually gives you some intuition on what a
So tau is basically the lifetime, which is tau is equal to 1 upon kf plus summation kt, which is the actual lifetime of the fluorescent molecule in the absence of bimolecular quenching. If tau is measured independently, then from the knowledge of KSV, the rate constant Kq for the bimolecular quenching state can be determined. It means as when the molecule is coming from for singlet state to the ground state, at that time it is emitting some radiation. Those are called as the fluorescent radiation, and the lifetime for which the excited molecule is being remain in that state is called as the lifetime. So if that time is known, then we can calculate the Kq value for the bimolecular quenching state. And for an efficient quencher, KSV, which is the Stern-Volmer constant, it comes nearly in the range of 10 to the power 2, 10 to the power 3 liter per mole. And tau, which is the lifetime of the fluorescent molecule, it is nearly in the range of 10 to the power minus 8 seconds. So as we know, Kq is equal to KSV divided by tau. So by calculating, we will get that the Kq value comes in the range of 10 to the power 10 liter per mole per second, which is of the same order as that of the encounter frequency as calculated in the cage effect. So that is the collision solutions. So in such cases, quenching is diffusion controlled and is obtained directly from the expression, that is 6.4, which we have already seen. So here they have given a table where the Kq values for anthracene molecule is being given for A, B and B values, C values are there. First A value is for oxygen quenching, B is for concentration quenching, and C is for the calculated from the equations 6.4. So all the values are being given there. Now, as before that video, I have told you that there are certain deviations. It means there is a competition between static quenching as well as the dynamic quenching. In case of static quenching, the decrease in the fluorescent intensity is independent of the lifetime as well as the diffusion coefficient, while in case of dynamic quenching it is dependent on both the values. So let's see these slides. Deviation from Stern-Volmer relationship may arise if static quenching is present, and the dynamic and static quenching can be distinguished by the following mode of actions. So here firstly, in case of static quenching, A molecule will combine with Q and it will form a complex AQ. So A is combining with Q and forming a complex AQ. So this is the static quenching where the complex is being formed in the ground state. Now this complex may absorb some radiation, and after absorbing the radiation it will form an excited state complex, and the excited state complex which is formed, it is called as excitase, and it has the ability to emit the radiation or not to emit the radiation. So it may be radiative or it may not be radiative. And in case of, we will see this, that is A plus V Q will form a complex AQ, and that complex will absorb the radiation and it will form a complex AQ star, and that exciplex may be radiative or it may not be radiative. Now let cannot be the molar extension coefficient for the formation of the complex AQ. So equilibrium constant can be given by concentration of product to that of concentration of reactant. So K0 will be equals to concentration of product to that of concentration of reactant terms. Let alpha be the fraction of radiation which are being absorbed. Now out of those amount of radiation which are being given, let the alpha be the amount of the fraction of radiation which are being absorbed by the complex. So alpha will be given by epsilon dash, which is a molar extension coefficient. That is, it is the ability to absorb the radiation by a particular molecule, and that ability is dependent on the structure of the molecule as well as its chemical composition. So alpha will be equals to epsilon dash, that is the ability of the AQ to absorb the radiation. So it will be equals to K0 times Q, as well as for A it is epsilon, and for again Q it is epsilon dash K0 times Q. So just simply, if the let's take the assumption that epsilon is equal to epsilon dash. So in that case, what will happen if you take it as epsilon dash? So epsilon plus epsilon dash will get cancelled out and 1 remain constant, and so K0 times Q divided by 1 plus K0 times Q. So here we will get the equation that alpha is equal to K0 times Q divided by 1 plus K0 times Q, and epsilon, if epsilon is equal to epsilon dash, where epsilon and epsilon dash, these are the molar extension coefficients of A and AQ respectively at the wavelength of excitation. Now if the complex is non-fluorescent, now if the complex formed is in the second case where A plus Q forming, it is giving the heat energy, which is the complex is not fluorescent, then in that case only the fraction, that is 1 minus alpha, is being absorbed and is used for fluorescence emission. And for small alpha and epsilon is equal to epsilon dash, the decrease in the fluorescent intensity, that is, this is the fluorescent intensity in the presence of quencher, which will be less than that of the fluorescence intensity in the absence of quencher. So F naught minus F divided by F, that is the decrease in the fluorescence intensity totally. It will be equals to KSV plus K naught. KSV, these are the equilibrium constants for the collisional quenching as well as the static quenching steps. So plus KSV into K naught Q square. So if we plot a graph here, firstly before plotting graph, here this is the Q and this is the Q square. So taking out the common out from this Q and taking it on the left hand side, the quantity those remains are addition of KSV plus K naught and product of KSV plus K naught times Q. Now if we plot a graph of F naught minus F divided by F naught divided by Q, it is called the quenching constant. The total quantity, that is F naught minus F divided by F, total quantity divided by Q, is called the quenching constant. It varies linearly with the concentration of Q. It means if it is plotted on the y-axis and this quantity is plotted on the x-axis, we will again get a straight line graph like that of the Stern-Volmer equation, and in this case the intercept, which is 1 in case of Stern-Volmer equation, here that intercept changes to KSV plus K naught value, and slope, which is only the Stern-Volmer constant in case of Stern-Volmer equation, it will be the product of KSV plus K naught, which is the collisional constant as well as the static constant. So the expression becomes more elaborate. This expression, it will become more elaborate if the complex is also emitting in the ground state also. So the expression becomes more elaborate if the ground state complex also emits after excitation or the fluorescent complex are formed in the excited state. So exemplars formation or emission they have occurred. Now this is about the if static quenching is present, where we have seen A plus Q forming the complex AQ. Complex AQ is absorbing the radiation. It is getting to excited state, and it has the two possibilities that it may emit the radiation or it may not emit the radiation, and from that we have to first detect the equilibrium constant, and equilibrium constant will be this value, and if alpha is the amount of radiation which is being absorbed by the complex, then in that case it will be related to the molar extension coefficient, and from that molar extension coefficient you got this equation, that is k naught q divided by 1 plus k naught q. Now if alpha is equal to this value comes, if alpha becomes equals to epsilon, it becomes equals to epsilon dash, where epsilon is the molar extension coefficients for A and AQ respectively, and molar extension coefficient is basically the ability of the chemical to absorb the radiation, which is dependent on the chemical structure as well as the chemical composition. So if the complex which is being formed, it is non-radiative in second case, this expression is for the first case, and now if for second case, if the complex is not radiative, then in that case F naught minus decrease in the fluorescent intensity, it will be equals to this value, and here Q and Q will come out common, and you will get this expression. And if you plot a graph, it will be a straight line, but the intercept which is 1 in case of Stern-Volmer equation, it comes to be KSV plus K naught, and the slope which is only KSV in case of Stern-Volmer equation, it comes to be KSV plus K naught. So these are the deviations from Stern-Volmer equation if static quenching is being present. Now the second case, if the static quenching is absent, then dynamic quenching may be present. What is dynamic quenching? Where the two molecules are at a larger distance. We have seen this diagram in the first video, where this is for the, that is, this is your quencher and this is your fluorescent molecule, which, and the distance will give the area of cross section, and that area will be calculated from the volume. That area will give us the volume. So if the quencher molecule are present near the fluorescent molecule at the moment of excitation, then the initial quenching before the steady state is being achieved, and it leads to the non-steady state turn in quenching expression. So a sphere of transient quenching of volume V can be defined as V is equal to 4 pi p r square under root of d2, where p is the probability of quenching, r is the encounter distance, d is the diffusion coefficient, which is the sum of dA and dB, and tau is the fluorescence lifetime. So based on this model, we can write the ratio of fluorescence in the absence of quencher as well as fluorescence in the presence of quencher. It will be equals to F e to the power minus k dash times q, where k dash will be equals to v times n, and placing the value of v, you will get this expression, that is 4 pi n p r square under root of d2 into 10 to the power minus 3. So the total quenching consisting of transient. Now just watch here, they are giving the idea about the total quenching first. So in case of total quenching, which will be the sum of transient quenching as well as because of its steady state contributions. Here they have sent non-steady state term in the quenching expression. So total quenching is basically the transient quenching as well as its steady state contributions. So the total quenching will come up to be F divided by F naught is equal to e to the power minus k dash times q divided by the steady state contribution will be 1 plus ksv times q. Now in case of weak quenching, for weak quenching, this expression will becomes this one, where F divided by F naught is equal to 1 divided by 1 plus k double dash times q, where k double dash is nothing but it is equals to k dash times k dash plus ksv, that is k double dash is equal to k dash plus ksv. Now just simplifying this equation can be simplified in this form, that is f naught minus f divided by f is equal to k double dash times q. So k double dash is nothing but ksv plus k dash So you will get this expression. Now placing the value for k dash, you will get this expression, and in this expression you can find that that expression, that is decrease in the fluorescence intensity, is dependent on the diffusion coefficient factor as well as the lifetime factor. So this is your expression last for the weak quenching. F naught minus F divided by F naught is equal to 4 pi n RAB D2 1000 in bracket 1 plus RAB divided by under root of D2 times Q. So here we have placed the value of K only. So lastly, what we found that the quenching is dependent on D value as well as tau value in case of dynamic quenching, which is independent in case of static quenching. So just read this, that assuming P is equal to 1, the transient quenching accounts for the deviation from Stern-Volmer relation in a manner similar to that of the static quenching, as we have seen, but K dash is proportional to root D and lifetime changes with the quenching. Here in case of dynamic or transient quenching, that K dash value is dependent on tau value, D value as well as the tau value, while in case of static quenching it is independent of D value as well as the lifetime of the fluorescent molecule. And this is all. What is the deviation from the Stern-Volmer? If it is in case of static quenching, there will be the instead of just KSV, there is some term which is being added. Instead of intercept 1, we are getting the intercept as KSV plus KQ, and instead of slope only KSV, we are getting the value of KSV into KQ. And in case of dynamic quenching, we can see it is dependent on the factor of, that is D and tau factors. And so this is all. Just watch the video twice so as to learn the concepts very easily. There are only three things to be learned: what is Stern-Volmer equation and what are the deviations. Stern-Volmer equation, phi f naught divided by phi f is equals to 1 plus KSV times Q, and this is the expression which is giving some deviation because of some components. If there are static quenching present, if there is dynamic quenching present, so what are the derivations? Those have to be given only. And this is only the thing. Just you can go through 3 slides. First, the equation for Stern-Volmer equation, and then the last 2 slides which are being important, on which this question will be asked. The question may be asked as, what is Stern-Volmer equation? This will be this question, or another equation will be, what are the deviation if static quenching is present, or another question will be, give the Stern-Volmer equation and what will be the deviation if dynamic quenching is present. Those have to be only. So this is the quote from Brahma Kumaris: people don't incite us, they give us their opinion based on their sanskars and not ours. We take their words and make them our identity and then use that identity to create hurt. So later they speak what they want to speak, but take only what you like. Thank you. Watch the video and share it.